We have learned how to find the zeros of a given polynomial. Now let us tackle the reverse problem. How do we form or construct a quadratic polynomial when we are given its zeros? Suppose we are told that the sum of the zeros is s and the product of the zeros is p. Then the required quadratic polynomial is p of x equals k times the quantity x squared minus s times x plus p, where k is any non-zero real constant. Why does this formula work? If alpha and beta are the two zeros, then the factored form of the polynomial is k times x minus alpha times x minus beta. Expanding this product gives k times x squared minus alpha plus beta times x plus alpha times beta. Since the sum of zeros is alpha plus beta equals s and the product is alpha times beta equals p, we immediately get k times x squared minus sx plus p. The constant k can be any non-zero real number and represents a family of polynomials, all sharing the same zeros alpha and beta. For the simplest polynomial we usually take k equal to 1. For example, suppose the sum of zeros is 4 and the product is 3. Then the quadratic polynomial with these zeros is x squared minus 4x plus 3, which factors as x minus 1 times x minus 3. You can verify that 1 and 3 are indeed its zeros with the given sum and product. We now extend the relationship between zeros and coefficients to a cubic polynomial. A cubic polynomial has degree 3 and the general form is ax cubed plus bx squared plus cx plus d, where a, b, c, and d are real number coefficients and a is not zero. A cubic polynomial can have up to 3 zeros. Let us call them alpha, beta, and gamma. 3 important relationships connect these 3 zeros to the coefficients. Relationship 1 is the sum of all 3 zeros. Alpha plus beta plus gamma equals negative b divided by a. As with the quadratic, the sum carries a negative sign on the coefficient b. Relationship 2 is the sum of products of zeros taken 2 at a time. Alpha times beta plus beta times gamma plus gamma times alpha all equals c divided by a. This is the sum of all possible pairs of zeros multiplied together. Relationship 3 is the product of all 3 zeros. Alpha times beta times gamma equals negative d divided by a. Notice the sign pattern. The sum uses negative b over a, the pair products use positive c over a, and the full product uses negative d over a. This alternating sign pattern is easy to remember. These 3 relations are extremely useful for verifying zeros and for solving problems where some zeros are known and others must be found. Understanding them thoroughly will make many cubic polynomial problems straightforward to solve. Example 1. Count the number of zeros of each polynomial from its graph. Remember the key principle. The number of zeros equals the number of times the graph crosses or touches the x-axis. We are shown 2 rows of 3 minigraphs each. In the first row we have graphs I, 2, and 3. Graph I shows a parabola that just touches the x-axis at its lowest point, the vertex. It touches the x-axis at exactly 1 point, so it has 1 0. Graph 2 shows a parabola that crosses the x-axis at 2 distinct points on the left and right sides. It intersects the x-axis twice, so it has 2 zeros. Graph 3 shows a cubic-shaped curve that crosses the x-axis at 3 separate points. It crosses the x-axis 3 times, so it has 3 zeros. In the second row we have graphs 4, v, and 6. Graph 4 shows a straight line cutting across the x-axis at exactly one point. A linear graph always has exactly 1, 0, so this has 1, 0. Graph V shows a parabola whose vertex sits exactly on the x-axis. It touches the x-axis at just one point but does not cross it. This is a repeated root, giving 1, 0. Graph 6 shows a higher degree polynomial curve that weaves up and down, crossing the x-axis at 4 separate points. It has 4 zeros. Summary: Graph I has 1, 0, Graph 2 has 2 zeros, Graph 3 has 3 zeros. Graph 4 has 1, 0, Graph V has 1, 0, and Graph 6 has 4 zeros. Example 2. Find the zeros of the quadratic polynomial x squared plus 7x plus 10 and verify the relationship between the zeros and the coefficients. Step 1. Write the polynomial and identify the coefficients. We have p of x equals x squared plus 7x plus 10. Here a equals 1, b equals 7, and c equals 10. Step 2. Factorize by splitting the middle term. We need two numbers whose sum equals 7, the coefficient of x, and whose product equals 10, the constant term. Those two numbers are 2 and 5, since 2 plus 5 equals 7 and 2 times 5 equals 10. Now we split the middle term x squared plus 7x plus 10 equals x squared plus 2x plus 5x plus 10. Grouping x times x plus 2, plus 5 times x plus 2, which gives x plus 2 times x plus 5. Step 3. Find the zeros. Setting p of x equal to 0 gives x plus 2 times x plus 5 equals 0. So either x plus 2 equals 0, giving alpha equals negative 2, or x plus 5 equals 0, giving beta equals negative 5. Step 4. See the zeros on the graph. The parabola of y equals x squared plus 7x plus 10 opens upward and crosses the x-axis at exactly the 2 points x equals negative 2 and x equals negative 5, confirming our zeros. Step 5. Verify the sum and product relations. For the sum, alpha plus beta equals negative 2 plus negative 5 equals negative 7. And negative b over a equals negative 7 over 1 equals negative 7. Both match, so the sum is verified. For the product, alpha times beta equals negative 2 times negative 5 equals 10. And c over a equals 10 over 1 equals 10. The product is also verified. Both relationships hold perfectly for this polynomial.